Okay, so for the next two papers, we have the same presenter, so I'm going to introduce her both twice for the sake of the recording of the video. But Aman Ramadan is a research associate and lecturer at the Computer Science and Engineering Department at the University of Minnesota, where she collaborates with Professor Jili Zhang. Her research is centered around enhancing the scalability and reliability of 5G and next generation networks, and today she's presenting the work, well, can we see the title of the first presentation? Oh, it's coming up, okay. Presenting the Dissecting Carrier Aggregation in 5G Networks, Measurements, Quality of Experience, Implications, and Prediction. Yeah, let's go ahead.
Hi, everyone. Thank you for coming for our presentation. So unfortunately, Wei is not able to be here, so I'm presenting this paper on his behalf. So this paper is actually a collaboration between our university, Southern California, as well as Cisco Research. So as we know, 5G has been deployed in order to enable new emerging applications, such as video content delivery, AR, VR, as well as remote driving. And this is due to the high bandwidth that has been enabled compared to 4G, as well as the promised low latency. So usually 5G is implemented in different bands. So we have the low band, mid band, and high band. And each one of them will have different frequency as well as different coverage. So as we can see, the low band will actually have the highest coverage or the largest coverage compared to millimeter wave. And in each of these bands, we're going to split them into different channels, and these channels can be implemented using time duplex division or frequency duplex division. So for example, if you actually take band N25, you'll see that it actually uses the FDD, and it has paired channels for the uplink and downlink, one for each, compared to if we use N41, for example, which uses TDD. So both of them use the uplink and downlink the same channel, but on different time slots. This is all depends on how the spectrum is actually allocated, and it depends on the auctions and government regulation, and it differs actually from one location to another. So now I want to introduce what do we mean by carrier aggregation. So as we have seen, there are these many fragments of the channel, and each one of them could have limited bandwidth. So in order for carriers to improve their performance, then they resort to something like what we call the carrier aggregation. As you can see in this scenario, user will be able to actually connect to multiple cells through this carrier aggregation, and hence increase their bandwidth. And instead of just the individual bandwidths of each cell, now they can have a bandwidth of 160 megahertz. One of these are going to be the primary, which is used for data and signaling, and the other are going to be secondary for just data transmission. Carrier aggregation is also flexible in order to combine channels, whether they are within the same band, which we call intraband, or between different bands, which we call interband, whether these are contiguous or non-contiguous channels. And that's why operators are now resorting to deploy this carrier aggregation in their implementation in order to improve their bandwidth for their users. And we have seen that in US, all the major carriers are actually implementing carrier aggregation. However, there aren't a lot of measurements done in order to reveal what's the performance of carrier aggregation, its characteristics, and so on. So the recent work that maybe just listed was more than 2 years ago, and it didn't even focus on carrier aggregation, it was just marginally mentioned. And even the machine learning algorithms for throughput prediction, for example, they didn't even consider carrier aggregation, which makes them sub-optimized. Hence, in this work, we are actually focusing on the live commercial 4G and 5G network from the carrier aggregation in networks from the QoE perspective. And we are interested to answer these 3 questions. First, what are the characteristics and the impacts of carrier aggregation? how can we dissect the complexity of this carrier aggregation? And finally, can we actually develop a better throughput prediction algorithm for which considers carrier aggregation? And in order to answer these questions, we have actually conducted extensive in-field measurements for carrier aggregation for the 3 major carriers in US, AT&T, Verizon, and T-Mobile. As you can see, these figures show some of our setups. So we have user equipments, which are mobile phones connected to laptops in order to run more professional tools that give us access to the chipset logs in order to have more visibility in the physical layer. And on the right side, you actually see some of the routes that we have conducted our experiments. This is a summary of the data set that we have collected. So you can see we have accessed up to 86 4G channels and 44 5G channels, which actually lead to different carrier aggregation combinations. 511 for 4G and around 61 for 5G. You can also see we have used different mobility and mobile phones, different phones, frequencies, and so on. I'm not going to go more into details, so you can refer to our paper for more details about our methodology and data sets. We can actually notice from our measurements that carrier aggregation significantly boosts the throughput. On the left side, this figure actually shows that each of these spots, whether the user have access to one carrier component, which is one cell, or 2 cells, 3 cells, and so on. So we can actually see that most of them are able to connect to up to 4 cells at the same time. On the right, the figures actually show the performance when we have carrier aggregation versus where no carrier aggregation is deployed. And you can actually see how the throughput is significantly improved when we are able to connect to multiple cells at the same time. So these are in terms of megabits per second. However, not everything is going to be good all the time, so there has to be some challenges. And one of the challenges that we actually notice is the carrier aggregation introduces new variability in the throughput and complexity. So the left figure shows a time series of the throughput that we observed when we have each of these channels independently, one from N41 and one from N25. However, if we actually have carrier aggregation where it combines channels from both bands, then you can actually see that the throughput is much more variable. And now this has imposed the question, what will be the impact of this high variability on the different applications, for example? This figure shows the throughput data distribution for the different combinations that you can actually see. So you can actually see how complex that gets. And for example, the figure on the right shows the distribution a UE can actually receive while doing a driving experiment when it actually passes by different combinations through its way. So we can actually see that we end up with a multimodal distribution for the throughput. And this actually makes it very challenging in order to do throughput prediction. And let me add a little bit more to that challenges is that this actually changes instantly. So we can actually have 4 carriers, and then in 1 second, we can just go to no carriers at all, which means that the throughput is going to significantly drop. And again, another time, we'll be able to connect to like 3 carriers. So this adds to the wild fluctuation of the throughput that we receive and definitely makes it harder for applications in order to adapt to this fast varying throughput. And in order to test that, we actually used some video streaming application, or actually, first we used Vivo, which is an immersive XR application, in order to measure the impact of application when they actually deal with this varying throughput. So here, the y-axis shows the normalized bit rate when it's actually compared to the ideal scenario. And the x-axis shows the increase in stall time. And each of these dots represents one of the traces that we have. On the top right corner, you actually see this is the ideal QoE that we want to achieve. And this case was when we don't have any carrier aggregation, and we had the bit rate up to 375 Mbps, which is compared to the average throughput that we were getting from our traces. On the right, we have the same figure, but now we have 4 carrier components in our carrier aggregation, and which means that we have now access to a larger throughput, and that's why we scaled our experiments to have a higher bit rates up to 750 megabits per second. So you can see that with carrier aggregation, we are more closer to the ideal QoE. However, from the wide variation between the first dot and the large dot, and the second, and the first dot and the last dot to the left, you can actually see that these applications are not able to fully utilize this capability. There are some issues that still needs to be addressed. And hence, we actually came up to the conclusion that in order for these applications to have a better performance, we need to be able to better predict the throughput, given the awareness of carrier aggregation, and that's why we have developed our own mechanism, machine learning model in order to actually be able to predict this carrier aggregation throughput. And so first, we're going to model the throughput for each carrier component separately. And we're going to explain why this is actually the case. And the aggregated throughput for all the individual carrier components will be giving us the final throughput that the application will actually receive or the user will actually feel. And each of these, the throughput that is coming from out of each carrier component, will actually determine, or it will be based on the transport block size, which how much data we can actually send in a particular slot. And this depends on the number of resource elements, the maximum modulation order, the coding rate, the number of MIMO layers, and more or less this actually depends on the signal strength that will be received. However, another complexity that we actually noticed that not all channels are contributing equally to this combined bandwidths that we have. And this could be related to the different radio propagation of the different channels or the varying deployment factors of each channel. So now in order to see how we can actually relay the information for the different carriers, carrier components. So first, we're going to study if we actually have a primary cell in the same band as the secondary cell, both in N41. And now we want to understand the correlation between the throughput of each channel compared to the signal strength that's received. So we can actually see that for each one of them individually, they are highly correlated to the signal strength. Additionally, if we actually want to utilize the throughput and see how it's correlated to the signal strengths of the other cell, we can still see that they are still highly correlated, so we can actually utilize this information. Now the question is, can we actually say the same when we have interband, when we have 2 different channels from 2 different bands? So in terms of each one of them related to the signal strengths, that's still valid. So now we have the primary cell is in the N41 band, the secondary cell is in N25. However, when we actually try to predict the throughput of each of these carriers, carrier components compared to the signal strength that's received by the other cell, we find that they are Model 3 correlated. This is again shows the same thing when we have the time series, when we have the intraband versus interband. So simply, we can't actually utilize the signal strengths of one of these carrier components in order to predict the throughput for the other one. We also have complex and dynamic feature interplay. So basically, if we have carrier aggregation versus not, if we look into the number of MIMO layers, we actually see that When we have carrier aggregation, the number of MIMO layers actually decrease. If we do the same thing and try to compare the number of resource blocks allocated, again, we find that this number decrease as well. So in order for us to actually have this model, we need to model each of these components separately. We need to monitor the signaling events as well as do fusion learning in order to learn this feature interplay. And these are the features that we have used for our machine learning model. So it depends on the phone that we're using, signal, RRC messages, physical layer information, as well as the historic throughput. So we feed each one of them for a model in RNN, and we use the model events for the binary state vector in order to activate or deactivate one of these. Then we apply some fusion in order to learn the interplay and pass this to a multi-layer perceptron. And finally, we aggregate the throughput and compare that to the actual throughput in order to find the loss that we have and use this information in order to optimize the whole model. We compared our algorithm with these baseline data sets. And for more information about this, please refer to our paper. We use the root mean square error in order to compare our performance compared to the other baselines. And we found that our method is actually consistently superior than the other baselines on an average of 14% and maximum of 22% reduction in RMSE. This is a visualization when we are actually zooming in where the number of carriers are actually changing. So we can see that our model is actually the closest to the real life prediction. This one, we incorporated our BRIS model into this application, Vivo, as well as video on demand, by just removing their throughput prediction and having BRIS to replace that. So we find that in Vivo, we're able to optimize the bitrate as well as the stall time. And for video on demand, we're improving the stall time. So to summarize, we just showed the snapshot of carrier aggregation, its characteristics, and we explained some of its complexity of how we can actually determine that. We then presented our PRISM, which is a carrier aggregation deep learning based throughput prediction method. And we have shown some experiments and evaluation for how it's actually efficiently overcoming the other baselines. Thank you. So one more thing, Wei, by the way, is looking for internships as well as future jobs in academic and industry. So if you're interested, please reach out to him. And our data set will actually be online on the link we have listed in the paper.
Hello, so this is William from the University of Illinois at Urbana-Champaign. Thank you for such an intensive measurement. That's definitely take quite a lot of effort. So I have questions about how do the phone itself activate the carrier aggregation? Is it reactive to the type of application that the mobile phone use? For example, if I just use it for regular web browsing or just opening Facebook, will that carrier aggregations get activated or what? Yeah, do you know?
So we actually don't control when the carrier activation is on or not. What we can do is band locking.
Okay.
Yeah, so, and then we use this physical layer in order to see, to get the information about the carrier aggregation.
So I may help you explain.
Okay.
It also depends on the phone model. The
Yeah.
phone can support up to 4 carrier aggregation. If you have older phone that may not even
Support carrier aggregation,
I see,
yes.
I see,
yes.
I see.
And then you are asking the question, so these are the base station nodes.
Yeah,
So
yeah,
three
yeah.
cells, you would configure your phone, say,
I see.
using 3 cells.
I see, I see. I mean, like, that's kind of interesting because I think carrier aggregation will definitely consume more energy, right? And like web browsing, I mean, like there's some applications that don't require that amount of throughput. So I wonder whether the mobile operators knows that, okay, you are going to be like sending a lot of data, so I will activate get carrier aggregations. Or right now, I mean, like they will be just using carrier aggregation whenever it's possible, even though like your application don't need that amount of bandwidth. Yeah, but I think it's worth investigating. I think it's also interesting.
So I mean, basically, the cells oftentimes just configure, you have more cells, may not be transmitting into more cells.
Oh, I see.
Depends on how much data you buffer on the
I see. That's interesting. Thank you.
Takuya Fujashi from Osaka University, and yeah, interesting talk. And I wanna ask you about the QoE evaluation. And you discussed about the degrade the quality with a percentage. So, but I'm not sure what is a metric for measuring such kind of quality degradation. So I remember the Bible may use the structural similarity for measuring the quality between the original and the reconstructed XR video. But in the structural similarity, 5% may represent from the 100 to 95, it seems a really large degradation, but 90 to 85% may have the almost seems the similar degradation. So what metric you use for measuring the quality?
I think we were comparing the video that we have actually received based on this aggregated throughput compared to the ground truth when the actual Vivo is not using our Prism 5G. So just comparing the performance in terms of with or without our 5G throughput prediction, but we didn't change the Vivo implementation in itself. So it's still making the same decision, but we're just changing the throughput prediction component. And then it's just comparing how far we are from that ideal QoE when we actually know the ground truth.
I see, okay.
Hi, this is Chen Hao from CRHK at Hong Kong. Thanks for the talk. I understand that you use some radio information to predict the carrier aggregation behaviors, but to my understanding, there are not much phones support how to say to get such information. So for applications like mine, only get some higher level of information like throughput or latency, this kind of thing. Can they still model the carrier aggregation behaviors?
So as Zili mentioned, the older phones actually does not support carrier aggregation at all, so we can't use them. So we have to use the newer phones. However, we don't have access to this information from the phone itself, so we actually tether these to a laptop. And then on that laptop, we run professional tools. So the one we are using was XCal, and we actually purchased a license for that. So this gives us information into the physical layer, and from there we actually know information about the carrier aggregation and the number of components, cells, frequency, bandwidth, and so on.
Short answer, no. If you just try to use information from phones through the Android API,
Okay.
you can't do it. Right? So
So
you want to do it, for example, Samsung may adopt the technology.
yeah. Another question would be apart from the radio level information, what kind of information would be efficient or effective to predict such behaviors like a map of cell base station deployments or these kind of things? Will that be helpful to predict the behavior of carrier aggregation?
You wouldn't know